This is chapter 4 on what I call bivariate data. Bi means two, so two variable data. The textbook calls this describing the relationship between two variables. So this would be a little similar to algebra. You might have learned this in one of your algebra classes. We're going to talk about what are called scatter diagrams or scatter plots and something called correlation. So let's start talking about scatter plots. Scatter plots are used to compare two variables. So we can compare height and weight, GPA, and number of credits, all kinds of different things that we can compare. One variable is the explanatory variable, which we call that the X variable, and the other is the response variable, which we call the Y variable. Explanatory we kind of think of as input, and response is our output. So the explanatory variable goes on the x-axis, while the response variable goes on the y-axis. And again, this is very similar to algebra. Scatter plots can show several types of relationships. So how these two variables relate to each other. We're only going to focus on linear relationships, ones that make straight lines, although nonlinear relationships can exist. So if you took college algebra, you might have studied quadratic, cubic, square root, all kinds of different relationships. We're just going to focus on the ones that make a straight line. So here's an example of a scatter plot with the x variable and the y variable and all the data points. And this is a roughly linear situation. Here's another one that's linear in the negative direction. This is a nonlinear example. This is a quadratic relationship. Here's another nonlinear example. This is a cubic relationship. And here's another nonlinear example that has no relationship at all. The points are just all over the place. So we can have linear relationships, we can have nonlinear relationships, or we can just have no relationship at all. So again, we're going to focus on linear relationships. So we're going to use this set of data for all of chapter 4. It says to create a scatter plot for the data below, comparing the club head speed to the distance traveled for a golf ball. So how fast you swing the golf club and how far the golf ball travels. So I've kind of set up your scales for you. You've got your club head speed along the x-axis, that's your input, and the distance the ball travels on the y-axis. I've started just where our data are, so it's kind of zoomed in just to where our data points exist. So our first data point has an x variable of 100 and a y variable of 257. So we're going to go to 100 on the x-axis and 257 on the y-axis. And we put 1 point for this coordinated variable. Then we're going to go to 102 and go to 264. We're going to go to 103 and go to 274. Let's make nice big scatter plot points so you can really see it. This is a pretty big grid. We're going to go to 101 and plot 266. Go to 105 and plot 277. And there. Go back to 100 and plot 263. So it's okay for the same x value to have a couple different y values. Go to 99 and plot 258. And to 105 and plot 275. So this is kind of a small data set, but it makes it a little easier to work with. You'll notice that the points generally go in the positive direction, and they generally make a straight line. If you can put your pen or pencil down along the points, you can kind of see they follow a positive straight line. So we're going to focus on two types of linear relationships. So if the scatter plot shows a linear relationship, so if it shows that straight line, there can be a positive linear relationship. As the x values increase, the y values increase. Or there can be a negative linear relationship. As the x value increases, the response variable decreases. And one quick example of that is the horsepower of a car versus the miles per gallon. The more power the car has, the less fuel efficient it is. So if we look at our golf data scatter plot, as the x values increase, the y values increase. So the golf data has a positive linear relationship. So you can tell that straight from the scatter plot. As the x values go up, do the y values go up or down? Alright, so that's a scatter plot. That's pretty easy to do. And I'll show you how to make one in the calculator here in just a little bit. Let's move on to the linear correlation coefficient. This is an important value when we're studying scatter plots. So after we decide if the data is linear and either has a positive or negative relationship, we then want to ask the question, how strong or weak is that relationship? We answer this question using what is called the linear correlation coefficient. And your textbook gets into all the different ways to calculate the linear correlation coefficient. We just need to know what it represents. So the linear correlation coefficient is a numerical measure between -1 and +1. So it can be any number between -1 and +1. And it tells us the strength and direction of the linear relationship. We use the Greek letter lowercase rho, which looks like a letter P, but in Greek it looks a little bit more like a letter R. It's kind of hard to draw. So rho kind of looks like that. Greek letter rho for population correlation coefficient, and a lowercase English letter R for the sample correlation coefficient. I'll tell you now, we're never going to use rho. We're never going to have a population set of data. We're always going to have the sample correlation coefficient. So we're always going to use lowercase letter r. I just wanted to let you know that rho does exist if you happen to have all of the population's data. We're not going to have that. We're always going to have the sample. So we're always going to use lowercase letter r. So again, the textbook gets into how to calculate r by hand. We are not going to do it by hand. We're always going to use the calculator to find the correlation coefficient. So if you turn to your formula booklet, the first thing in Chapter 4 is the correlation coefficient, and it gives this big, crazy formula for calculating it. You might just want to make yourself a note to use the calculator for the correlation coefficient. I'm not going to get into how to do all of that by hand. Alright, so in your calculator, the first thing you want to do is turn what are called diagnostics on. To do that, in either the old or the new calculator, to do that you go to second, 0. Above the word 0 you see the word catalog, so second, 0. The calculator automatically puts itself in alpha mode. It might be hard to see. Alpha are all the letters above the buttons, the little A, the little B, the little C that are in green. So all those little letters are alpha mode. We want to go to diagnostics that starts with a D. So the button with X to the -1 power has a little D. We're going to jump down to the D's. Then we're going to keep going down with the down arrow to diagnostic on. You're going to hit enter and enter one more time until it says done. It's the same steps in the new calculator. You go to second. You know you've pushed second when you see the up arrow, and then you're going to push 0 for catalog. I don't know if the newer ones, yes, it does put it in alpha mode. You see the little A by the battery, alpha mode, and then D for diagnostic, and then down until you see diagnostic on, and you're going to hit enter twice until it says done. So you'll need to do this when you're in Chapter 4, turn those diagnostics on. They should stay on unless you reset your calculator. So either don't reset your calculator or just always turn them on. If they're already on, it's okay to turn them on again. It's no big deal. So make sure that they're on for what we're going to do. Then type your data into L1 and L2. Remember, that's stat edit. To get to this, we go to second, 0. So stat edit, type your data into L1 and L2. So I'm referring to the data from the golf data back on page 1. So I want you to put all the club head speeds in L1 and the distance traveled in L2. And make sure order matters here. Make sure each pair of values are across from each other when you put them on. So you're going to go to stat, enter for edit, put all your club head speeds in L1, all your distances in L2. Newer calculator, same procedure, stat edit, L1, L2. Make sure that it's the same number of data points in each. They should line up with each other and they shouldn't be off by 1. So type them carefully into L1 and L2. So that's step 2. And then the final step is stat calc option 4, linear regression. And it should say AX plus B. Your calculator uses a different option. I'll show, not your calculator, your textbook uses a different option. I'll show you. So if you go to stat, over to calculate. We've done one of our stats before. Now we're going to go down to where it says linear regression AX plus B. Your textbook, I believe, tells you to use option 8, A plus BX. But being in algebra, you guys remember the MX plus B formula, so I like option 4 better. So stat calc option 4. You're going to hit enter. On the older calculators, it assumes that your data is in L1 and L2. So you don't have to do anything, you just push enter. And the newer calculators, you have to make sure the X list is L1, the Y list is L2, the frequency list should not say anything. If there's something there, hit clear. Storing the regression equation we're not going to do, and you just go down to calculate. And then let it run. So again, we're choosing option 4, AX plus B. We're going to see that in 4.2. Right now what we're focused on is the last value, R. If R did not show up, that means your diagnostics are not on. So go back in the video and follow the instructions to turn diagnostics on. You should have this R value with the older or the newer calculator. So anytime if you're trying to get correlation coefficient and it doesn't show, go back and turn diagnostics on. Alright, so let's record the R value for our golf data, which is 0.94. Again, we usually round. I think generally they tell you to 2 decimal places. The homework might say more than 2, but 2 is enough. Get that glare to go down if I can. Alright. So we've got our R value. Let's talk about what that number represents, what that 0.94 represents. So how to interpret your correlation coefficient. The closer R is to +1 or -1, the stronger the linear relationship. So it's kind of like a grade out of 100%. So the closer you are to 100%, the better the relationship. The closer R is to 0 from either direction, the weaker the linear relationship. So there's kind of 3 levels of strength that your textbook talks about. And different textbooks have different cutoff points for this, but I'm using the points that this particular textbook uses. So any value, any R value between 0.8 and +1 is considered strong. It's kind of like getting a grade of 80 to 100%. So that's a strong relationship. Same thing for the negative. If it's between -0.8 and -1, that's also considered a strong linear relationship. Anything between 0.4 and 0.8 in different textbooks, some textbooks say 0.5, but this one says between 0.4 and 0.8 is called a moderate linear relationship. Same thing on the negative end. That's like making between a 40 and an 80 is considered moderate. linear relationship. And then anything between 0 and 0.4, and again, some books say 0.5, but somewhere in there, between 0 and 0.4 is considered a weak linear relationship. On the positive or negative end, it's considered weak. So let's think about our golf data and what kind of relationship it has. We know that it's linear. We saw that it's made a straight line. We know that it has a positive linear relationship. And the R value kind of gives a grade to how strong that linear relationship is. So for the golf data, there's a strong linear positive relationship between whatever the two variables are you're talking about. In this case, it's club head speed and distance traveled. So there's 3 words that we're looking for when describing a scatter plot. Strong, moderate, or weak, that's the first word. The second word is linear. Remember, we're only interpreting linear relationships. And then positive or negative. So the strength, the shape, which is linear, and the direction, positive or negative. So those 3 words are what I'm looking for when you're describing or interpreting your correlation coefficient. So strong, linear, positive relationship between club head speed and distance traveled. So you always want to talk about your x variable and your y variable, whatever those are for the situation. All right, let's finish up 4.1. I want to show you some visual representations of the correlation coefficients. I want to show you weak, moderate, and strong. So at the top of page 3, we go through just some of the properties of this linear correlation coefficient. This looks like a big scary list, but all of it is pretty reasonable. We've kind of already talked about all of it. So it says the linear correlation coefficient is always between -1 and +1, inclusive, which means it can be perfectly negative, it can be perfectly positive. If R equals +1, then a perfect positive linear relationship exists. If R is negative, then a perfect negative linear relationship exists. That doesn't happen very often, but it can. The closer R is to +1, the stronger the positive relationship between the two variables. The closer it is to -1, the stronger negative. We've already said all these things. It's just one big list. Property 6 is very important to understand. If R is close to 0, then little or no evidence exists of a linear relationship. The R value only measures a linear relationship. So it's a linear correlation coefficient. So R close to 0 does not imply that no relationship exists, just not a linear relationship. It could be quadratic, cubic, exponential. It could be all kinds of different relationships. So make sure property 6 makes sense to you. Property 7, the linear correlation coefficient is unitless, kind of like a z-score. So the unit of measure plays no role in the interpretation, again, kind of like z-score. The correlation coefficient is not resistant. Therefore, an observation that does not follow the overall pattern of the data, which is what we call an outlier, could affect the value of the linear correlation coefficient. So having a data point off track is going to impact the correlation coefficient. So property 6 and 8 are the ones you really want to make sure make sense to you. So here's some visuals of different correlation coefficients. Here we have a perfect positive linear relationship. Every single point is exactly in a line. Here we have a strong positive linear relationship where they're pretty close to a line. Here we have a moderate positive linear relationship, so kind of all over the place, but generally going in the positive direction. Here we have a perfect negative linear relationship, a strong negative linear relationship, and a moderate kind of all over the place, but generally going in a negative direction. The bottom two, here we have no linear relationship. Your R value is close to 0. The points are all over the place. Here we have another no linear relationship. Again, the R value is close to 0, but you can see that they do have a pattern. It's just not linear. So those visuals, I think, are helpful to really understanding what the R correlation coefficient measures. All right, the last part of 4.1 is to determine if a linear relationship exists. This is kind of proof of linear. So let's say you can't see the scatter plot and you still want to know if it made a pretty straight line. So to do this, we compare our correlation coefficient to what's called the critical value based on sample size. That's given in Table 2 of your formula booklet, which I believe is page 5. Let's go to page 5 real quick. This is right under the random digit table. Table 2, the critical values for correlation coefficient. So here you have different sample sizes, 3, 4, 5, all the way to 9. Sample sizes continue and continue and continue. So all the n's are one big column. They're just stack them to save space. Then you have what we call the critical value. This number is telling us what kind of correlation coefficient we should get based on our sample size. So based on sample size, what kind of correlation coefficient should we get? So if our correlation coefficient, and I'm talking about the absolute value, just the number itself, is greater than the critical value, then we can say a linear relationship exists. So instead of looking at the scatter plot, if I want proof that the values make a linear scatter plot without looking at it, I can use this critical value. So you have a critical value, positive or negative, it doesn't matter. And if the correlation coefficient is outside or beyond the positive or negative critical value, wherever you are, if it's bigger than that, then a relationship exists. If it's smaller than that, then it does not. So let's look back at our golf data. This is a pretty easy practice. Let's go back to our golf data. Our R value was 0.94. Let's look at the critical value based on the sample size. So let's count up how many we had in our sample. We had 1, 2, 3, 4, 5, 6, 7, 8 in our sample. So if our sample size is 8, now we're going to look at 8 on our chart, and it says that the critical value should be at least 0.707. So because 0.94 is greater than 0.707, and it doesn't matter if it's positive or negative, it's just the number itself, because our R value is greater than the critical value, we can say yes, a linear relationship exists. So if we did not make the scatter plot, we can use this check to make sure it's linear. All right, so it's easy. It sounds kind of intimidating, but it's easy. You just use your chart. The last thing I want to talk about is association versus causation. And I think there's a video, I'm not sure if I posted it. It's a little confusing, but there's a gentleman that tries to explain the difference between association and causation.